Hello and welcome. My name is Hugo Curry and I'm a Year 12 high school student at the Riverina Anglican College in Wagga Wagga, Australia. This is a series of brief interviews with some of the most amazing physicists from around the world. I'm passionate about physics and will pursue a career in physics and engineering, so I'm honoured to be able to ask a few questions of some inspirational physicists. I really want to thank them all for generously taking the time to chat and, importantly, passing on their rich insights. Hopefully other students with an aptitude for physics can take inspiration and guidance from their experiences and insights to shape the next generation of physicists. Today I'm speaking to Professor David Townsend. Professor Townsend worked as a particle physicist at CERN before becoming a medical physicist. He was instrumental in developing the first positron emission tomography systems and invented the PET-CT system that combined PET imaging with CT imaging, Time magazine's Invention of the Year in 2000. Professor Townsend received the prestigious Paul C. Abersold Award from the Society of Nuclear Medicine and Molecular Imaging in the US for 3D PET and PET-CT development. Professor Townsend has a long list of other prestigious awards and invited lectureships, recognizing his extraordinary contribution to medical physics. He has worked as a medical physicist in Geneva University Hospital, University of Pittsburgh, and the National University of Singapore, but comes to us today from Whistler in Canada. Thank you for taking the time to share your thoughts and experiences.
Thank you for inviting me.
Well, good. So firstly, what drew you to a career in physics and what excites you about physics?
Well, this was many years ago. I guess I had to make a choice between physics and other topics, and at the time, I didn't really have a huge motivation to go into physics. It was just something interesting. I didn't, for instance, disassemble radio sets or anything back when I was a kid. But I just thought I'd see what it was like. And so I studied physics in the, what is the sixth form at school in the UK. And then decided to apply to universities to study physics further. I guess I found it interesting. I think one of the key points is I had a very good physics master who motivated us. The physics master was very motivational, and he also had strong links with one of the good universities in the UK, the University of Bristol. And so I applied to the University of Bristol, and among others, and then followed an undergraduate degree, bachelor's degree in physics at the University of Bristol. And then at that point, I had the opportunity to spend a summer at the European Centre for Nuclear Research in Geneva, because in our third year, final year in Bristol, we had lectures from one of the top physicists at CERN. And out of the year that he lectured to, so he gave just a series of lectures. He wasn't one of the lecturers at Bristol throughout my time there. He just came and lectured a few lectures to sort of inspire the third year. And as a result of that, he made arrangements for two students out of the third year to spend a summer as summer students at CERN. And so I was luckily one of the two students that was selected. So I moved to CERN for the summer. Spending time at CERN was, again, highly motivational, interested me, obviously, in elementary particle physics. I was fortunate enough to work in the group that included Simon van der Meer, who got the Physics Nobel Prize with Carlo Rubio, forget which year it was. So I got to meet some really top people, and decided then to pursue a doctorate, a PhD in physics. So I applied to the University of London, was accepted at the University of London. So I then spent 3 years studying particle physics, 3 to 4 years studying particle physics. Before I had felt after I'd worked at CERN that that's where I wanted to work. So I applied for a position at CERN And the first one, I wasn't successful, but they retained my name. I spent a few months back at the college I was studying at in London in association with Imperial College. And then I got a letter from CERN saying there was another position available, and I applied for that. And so in about 1970, I was recruited to CERN, and I spent almost 10 years at CERN. So it was at a period, a very sort of exciting period in particle physics with new accelerators starting up. But after a few years doing particle physics, I began to feel that one was just part of a huge team. The teams were getting bigger. When I did my PhD in particle physics, we were a group of maybe 8 people doing an experiment. But as the experiments got more complex, the accelerators got more complex, the teams got bigger and bigger, and you could easily have 50 to 100 people in a team. So you kind of didn't feel you had much of an identity in that group, even though it was obviously exciting physics to be working on. And that's when I was fortunate enough to meet or to work with somebody who was interested in applying CERN technology to medical applications. And so I, like many people during that period of the 80s, I kind of translated from particle physics into medical imaging.
Yeah, nice. It's certainly very interesting reading about your career and everything you've done. I mean, CERN is on my bucket list. I definitely want to go and just have a look one day. It sounds amazing. Yeah. So what do you see on the horizon that would inspire the next generation of physicists that's kind of up and coming, I guess?
Well, I mean, most of my career has been in medical imaging, since I guess I spent about 8 years applying what I'd learned as a postgraduate to developing software for particle physics experiments, because I was really in those days on the software side. And then when I moved into the medical applications, of course, I learned a lot more about the medical applications. So in terms of fundamental physics, I've been out of it for a long time now, and I've been much more in the applied side of physics. But and that honestly I've found much more inspiring. You can obviously you can obviously read about the field that you were in, and you don't forget a lot of the stuff that you were involved in day by day back when I was working at CERN, and I have friends at CERN. But really the area in which I've spent then most of the time since 1980 until I retired was really in the medical application field. And obviously I feel that has a lot of interest and a lot of potential. And I chose in 1975 to go into positron emission tomography, because I was approached by a CERN physicist who was building a small detector that could detect the 511 keV annihilation photons from positron annihilation. And he was applying it to a different field, to solid state physics, which was his background, whereas mine was in particle physics. But CERN brought together physicists from many different disciplines, because developing detectors, detector materials, this is all part of the field. In fact, at the time I was there would have been 4,000 people at CERN, of which maybe 100 were actually employed as particle physicists. Wow. The rest of the people were basically to support the experiments that were thought of and devised by a very small number of physicists that were employed. I mean, we were all employed as physicists, but as a particle physicist leading an experiment, there were very few. Most of the people that did that were from outside universities. So if you visit CERN, you'll see that there is often 1,000 visitors. Well, not at the moment because of COVID, but there's usually 1,000 visitors on site at any one time from all the different universities from the 20 or so countries that contribute to the CERN budget, plus the US that doesn't have any more an installation at that level as the LHC or the other CERN accelerators. So it's a huge melting pot of people from all sorts of different disciplines. So I teamed up with this solid state physicist, Alan Jevons, and we started to look at applying this technology to positron tomography. And then that's what really led me down this path. But the point I'm making is that I decided to go into this field in 1975. And as of today, as you probably know, it's a thriving field. It's been taken into the clinic, so it's used routinely for clinical imaging and nuclear medicine. There are new devices being developed all the time. I know Dale Bailey and Steve Meikle are going to be getting a total body PET imaging system in Sydney. So it's continued to develop, but in a sense, as a field, it's underachieved. So from a technological point of view, the most amazing instrumentation has been developed over the 3 or 4 decades since it was first proposed for the clinic. But in terms of applications, there is so much more that can be done with it. And what my colleagues and I have discussed is the lack of sort of young people going into this field. And that's obviously a concern. I mean, a lot of the meetings that we have that I used to attend before I retired, it was the same sort of people that always came to the meetings and gave the talks. And there was a distinct feeling that young people were not being attracted and motivated to go into this field where you take some technology, whatever it may be, and apply it to an application that has an impact on the way medicine is practiced.
Yeah, I think that's very interesting how you were saying where are the young people? I know from my own perspective, just a school kid in like country Australia, we get told about all the engineering opportunities and physics opportunities and chemistry opportunities, but nowhere has there been said anything about medical physics or even biomedical engineering. So you've had such an amazing career. I'm interested to know what's been the highlight.
Well, I mean, I guess the development of the combined PET-CT scanner was has to have been the highlight. But I mean, to emphasize, this was the result of many years of kind of doing other things that led up to this. So initially, I got into software. I was always more on the software side, but working in small teams. And so I was sort of working at CERN, but then got interested in developing software for positron imaging. And this was completely peripheral to what I was doing at CERN, but was, to me, turning out to be more interesting. And so I could develop computer algorithms for reconstructing images in parallel with developing computer algorithms for reconstructing particle tracks in a magnetic field. So it was, because CERN was a very open and very sort of supportive environment, you could do that sort of thing. So, I mean, it wasn't obviously a 9-to-5 type job. You could, you had a lot of freedom. And so beginning there, I then worked on these small positron imaging devices that have higher resolution. And we got one into the hospital in Geneva. I then left CERN and moved to the Cantonal Hospital, University Hospital, worked there for another 10 years or so on PET imaging, and developed a system that then triggered the idea, this would have been about 1990, triggered the idea that we could maybe combine PET imaging with something else. And the something else turned out to be CT. But I was really working in a hospital, Geneva Hospital, which is a huge hospital, but it's not, at the time, we weren't sort of a world center for medical imaging. But again, working in association with CERN, I was able to do more than I could have done if I'd just been at the hospital. So the two are, I don't know, 10 miles apart. And so we developed instruments at CERN that we then tested at the hospital. And this was a really unique opportunity in collaboration with the head of the department I eventually joined, who was the head of nuclear medicine. And he was extremely supportive of the PET work we were doing, even though at the time it had no clinical, it wasn't used clinically really anywhere. It was a kind of research tool. So we developed this sort of pre-PET-CT device, which was PET only. And then the idea came up to combine it with CT in about 1991. And then in 92, I was recruited to the University of Pittsburgh. And in arriving in the US, I then submitted a grant to develop PET-CT that was rejected totally the first time. And then I resubmitted it and it was accepted. So we were funded, and from 94 to 97, we developed the PET-CT. Now, it was not something that could have been developed purely at a university. So I was very fortunate that while I was working in Geneva, I was invited to spend a sabbatical at Hammersmith Hospital in London, which was a leading research PET center, research in terms of clinical research in the UK. And there I met people from a company in Knoxville, Tennessee, that was developing PET scanners. It was a commercial company, and there was like 3 in the world in those days. And it was a small company, 100 people. And so I got to know the people there very well. So when I moved to the University of Pittsburgh in 1993, I put together this grant to develop PET-CT, but with this company in Knoxville, Tennessee. And so over those 4 years, 94 to 97, 98, we built the first PET-CT prototype. And I guess that was sort of a highlight when the first patient was scanned on the first ever PET-CT scanner that I built in close collaboration with Dr. Ron Nutt, who was the co-inventor with me of the PET-CT. Now, at the time, we had we thought it was a good idea, but one thing you learn about the medical field is that it's very conservative. It doesn't accept new things easily. And so we didn't get a lot of support for what we were doing from the medical side. But as a technical and engineering project, it was very interesting, very exciting. Yeah, and in 1998, then we installed the prototype. In April of 98, we installed this prototype at the University of Pittsburgh Medical Center. And I guess in May of that year, about a month and a half later, we scanned our first patient. And then I presented the first images at the Society of Nuclear Medicine meeting in Toronto in June of 1998. And then that started to get the attention of the medical establishment. And there were definitely two groups of people, those that jumped on it and those that said it was a waste of time, waste of money, and was never going to go anywhere. And I was fortunate again to work with visionary people at the University of Pittsburgh that allowed us to test a prototype with patients. So in the 3 years from 1998 to 2000, we scanned about 300 patients on this prototype. Within 2 to 3 years, nobody wanted PET only, everybody wanted PET CT. So its adoption within the field was very rapid, much more rapid than is usual with new instruments. And so eventually, by about 2004, 2005, the company was not selling PET anymore. They were only selling a PET CT, as was General Electric and somewhat slower Philips, but eventually Philips also developed their own PET CT. And then over the last 20 years or so, there's been repeated generations of new PET CT devices. So there's about, I guess, 6,000 of them now in operation worldwide.
Wow, yeah. So talking about the PET CT system, and I think you've touched on this a little bit, I'm interested to know what inspired you and how do you take an idea like that from your imagination to develop it into a reality, I guess?
Well, that's a good question. And the answer to some extent is that to have a good idea, and we felt in 1990 that combining a functional imaging approach like PET with an anatomical imaging approach would give you the best of both worlds. And that was really the concept, was to put together the two systems. And we felt at the time, although it hasn't quite worked out like that we could simply replace, all CT would be done on a PET CT, because we were obviously PET physicists. And we felt that PET provided a totally different type of functional information to the anatomical information you got from CT, and that the combination of the two would tell you not only that you have something wrong, but also tell you where it is. And so that was the kind of inspiration behind it. But it began as an idea. So then to take it further, you need to have support from the people that are going to help you develop it. And for me, that was the company in Knoxville, because they could make PET scanners. They had set up a joint operation called a joint venture with Siemens in that would have been about 1987. So they'd had this operation for a few years, and that meant they were closely aligned with Siemens, and we convinced Siemens to provide us with, at no cost, an old CT scanner. So it's difficult to get started when you don't have anything. So at that point, we had an old CT scanner and a company that could make a PET scanner. And they were interested because Ron Nutt was a visionary leader of the company and felt the PET CT maybe did have a future. They were keen to assemble the first system at the factory in Knoxville. So we started to put together a team, and the University of Pittsburgh said, if you get a grant to do this research, then we'll support it. So the key thing was to get funding from peer-reviewed funding agency. And to get what is called a research grant, R01, to build the PET-CT was the key step in taking it further. Because if you don't have the support of your peers in doing this, then it's very difficult to convince a company to invest in it. Not impossible, it depends on the company's business model to some extent, but unless you have independent funding and are recognized then as a researcher, it's very difficult to kind of get off the ground. But once we got the funding, then people started to contribute in kind, like the CT scanner, some of the PET components, and then the thing started to gather momentum. It still took 3 years to put it all together. There's a lot of hurdles we hadn't anticipated when we submitted the grant. But from the time we got it funded to the time we've put the prototype in the hospital took us about 3 years. Having the right team of people, I had a very good PhD student working on it, Thomas Byer, and very strong support from Hammersmith Hospital, even though we were doing the work in the US. Terry Jones was very supportive of it, and it was at Hammersmith that I met Dale Bailey and Steve Meikle, because they did some sabbaticals at Hammersmith. And so we had a sort of small team of people that were quite visionary. We had funding, and we had a company that was prepared to take the risk of helping us to put this together, make a prototype, and ship it up to the University of Pittsburgh. And at the University of Pittsburgh, we had a receptive group of physicians that were just curious to see what would happen. And was it a viable concept? Was it interesting? And so once we had it installed, then you have to sell it, not financially, but you have to sell the concept to the physicians. But the key to getting it to move forward was to get referring physicians involved. And we got surgeons interested, because surgeons are hands-on people that need the images to see what it is they're going to do when they open the patient up, or what sort of operation they need to envisage. So it was key to the success of the device.
Is there anything in physics or medical physics that is important or contentious that you would like to see the next generation of physicists work on?
Well, I mean, a lot of it is contentious. As I said, there was a lot of resistance to what to us seemed like a good idea at the time. And one thing to add to what I've just said is, apart from having a really good group of people and to work with good people like Dale and Steve and people like that, it's important to just have luck. I mean, we just happen to be, if you like, in the right place at the right time. If we'd come out 5 years earlier, I doubt if anybody would have cared about it. And once PET kind of got going, it might have even been harder to get PET-CT, because you now had two modalities. Why complicate things by putting them together? But we kind of slipped PET in under the CT umbrella, and then suddenly PET was paid for, so we're good to go. And so it was a very it was very fortunate that this all came along at the same time. Now, in terms of what is exciting to be working on, over the two decades or so that these instruments have been developed, we now have very high performance compared with what we had originally. Very high performance imaging device, PET-CT scanners from the imaging vendors, GE, Philips, GE, Philips, and Siemens. And then the total body imaging came along, developed by Simon Cherry and Ramzi Badawi at UC Davis, which had always been a dream, because as you probably know, when you inject a radioactive isotope into a patient, it does target to some extent the pathology that you're interested in, but it still goes throughout the body. And so if you're only imaging a little bit of the body, you're wasting all the rest of the radioactivity, which is different to CT, because in CT, the radioactive source is outside the patient, and therefore you're just imaging the area where the radioactive source is focused. So it's a very different approach, because you've got the radioactivity injected in the patient. Ideally, you want to cover the whole patient with a tube, and that's what this total body PET has finally achieved after many, many years of hoping for it. So now we have total body PET, and this is the sort of cliche as a game changer, but it really is made a difference, because now you're able to image all the organs simultaneously, with short time frames, watch them dynamically. And something we've never been able to do before is watch the interaction between different organs dynamically in the same patient. Yeah. So this is really, after all these years, we're now at a new stage with applying this functional imaging modality to new clinical problems. And that's what's going to be, there's huge potential there. And they recruit postdocs and so on into centers that acquire these devices.
Yeah, that does sound very interesting. Yeah. So final question.
Yeah.
Do you have any final pearls or pitfalls to offer high school students that have an aptitude for physics?
Well, certainly if you have an aptitude for it and an interest in it, then it's a field that offers so much. And as with the medical field, you can go in as a medical student and then specialize in many different areas. Physics is somewhat similar. So I chose to go into particle physics and then to translate into medical imaging through the application of particle physics instrumentation to medical imaging. What motivated me was the possibility to take technology from one field and apply it into another field. So then you get the opportunity to learn a whole lot more about another field, like, medicine. Even though you're not a physician, you do learn a lot about some of the problems they have, some of the challenges, and also some of the, they can be difficult people to interact with. So it's important to realize that you're kind of helping them to help their patients. But it means you get to work with different disciplines. And the field that I was involved in allowed us to work with chemists, radiochemists, physicians of all different disciplines, different physics people, engineers, computer scientists. I mean, it was the one field which brought together skills from many, many different disciplines. So that's worth considering if you have somebody, if you're interested in physics, but also, if you want to work with people from other disciplines, then a specific application to another field is very rich in being able to do that and lead you to learn more about things than just the interaction between particles, which is, now that's combined with astrophysics and has also brought in other disciplines. But I just found working with physicians is a challenge, but it's also very rewarding when you can help them and you actually meet patients that, thank you for what you've contributed, because they feel that they were imaged early and their medical problem was found and treated, and they're alive today because of the imaging device that you built. That's in the end, that's very rewarding.
Yeah, I bet. Well, thank you so much for such a rich insight into the world of medical physics. I really appreciate you taking the time to inspire the next generation of physicists, and I'm sure that the people that listen will share my appreciation. Yeah, thank you so much.
Sure. Well, if there's any follow-up or any further questions, I'm sure we can arrange you can email me, or we can fix up another session. This worked very well, and it's very easy to do.
Yeah, cool. Yeah, thank you. Really appreciate it.